Alexei and all the organizers for inviting me here. It's a real pleasure. I'm especially happy to talk about this work, which was concluded just yesterday. And it's a collaboration between my group, we call ourselves Quantum Correlations, and some engineers at Nottingham who work in manufacturing metrology, typically classical. So we're hoping that eventually we might converge towards something that is useful for what they need in analyzing surfaces by using techniques from quantum metrology, which so far have been more or less applied, but still on the proof of principle level. So the work is about estimating separations of two sources. And there's been a lot of activity on this topic recently, since at least with the spike since 2 years ago, when it was demonstrated, as we will see later, that this Rayleigh's criterion that limits the resolution of classical direct imaging can actually be beaten by quantum measurements. And this was a series of works by Mankei Zhang and collaborators. And here we go a little bit further by considering a situation which is a bit more realistic. So points that not only have one separation, but they can have also an axial separation because they might lie on different image planes. And I hope I will convince you that this is interesting also from the point of view of applications to 3D surface topography. Okay, so in this talk we are going to briefly remind you and myself about the paradigm of imaging, just very, very simple things, and what is this Rayleigh's curse, as it's been called now recently, which stems from resolution limits due to criteria such as Rayleigh, Sparrow, Abbe, and so on. And then we're going to give super fast revision of quantum metrology. This is going to happen all over again during this workshop, I guess. And then we focus on our problem, which is estimating axial and angular separations and centroid coordinates for 2-point sources. So it's 4 parameters, multi-parameter estimation. And then I will discuss issues such as compatibility, what is the measurement we should do, and then how to move this towards application. This is pretty much still work in progress. Yeah? So I hope that I get some ideas also from the experiments here. Okay, so imaging. Imaging is very important for lots of applications. So progress in high-resolution imaging has enabled breakthroughs in medical, diagnostic, astronomy, and recently is also driving applications in all sorts of applied sciences. Yeah? So you need to very precisely be able to measure and map features of living systems or artificial systems in order to improve the quality of your manufacturing process, or in order to cure people or diagnose brain diseases and so on. So very simply, if we want to estimate, if we want to consider this problem of 2-point sources, they can be 2 distant stars, or they can be, for instance, 2 emitters that we put onto a molecule and we apply fluorescence spectroscopy, and we want to resolve them. Resolve them means determine the distance between them. If they're aligned on the same object plane, then there's only this angular separation that we want to investigate, but there can be also the coordinate of the centroid, but this is typically easy. More or less you see some blurb and you can localize that, but to understand whether there's 1 or 2, or if it's 2, how far they are from each other, especially when they're very close, it becomes difficult. It becomes difficult when you use techniques that only rely on measuring the intensity at the end. And this is what this Rayleigh's criteria, this is not Lord Rayleigh, it's some guy from One Piece, manga, pirate manga. But Lord Rayleigh basically said something like that. So, of course, you have a lens and then you have your image plane. Every spot will, due to diffraction effects, will arrive there. Every point, even if it's a point source in your model, will arrive on the image plane as a blurred spot. So it will diffuse. And similarly for the other thing. And these 2 spots on your screen will have some overlap. And this depends on the point spread function, which is also due to the specifics of the lens and the imaging system. But roughly the idea is you can resolve by direct imaging these 2-point sources if their separation on the image plane is at least of the order of the width of the point spread function, which basically means the wavelength of the emitted light normalized by the mean photon number. So if it's above, then you see things very clearly. If it's below, then you start to see that they overlap with each other. So we can, for instance, see here, these are well resolved because this separation here is bigger than, let's say, the standard deviation of this. In this case, it's a Gaussian beam. here is the Rayleigh limit, where the peak of one of the maximum of one of the wave functions here coincides with the first minimum of the other. And so Rayleigh said, if you go below this, then you are not able to resolve it anymore. And he made some calculations, and it seemed to go well as a criterion for astronomy, classical microscopy, and so on. So if you are below, then you see just this blur spot, and then you cannot resolve. But is it really the case? So if we want to determine whether something can be resolved or not, if we want to determine the ultimate limitations, the most fundamental ones, then we have to take into account a complete quantum mechanical description of the imaging process. And in this case, we have to make clear what is quantum here, because the source is classical and incoherent. The only thing where quantum mechanics can help is at the measurement stage, because so far we're probably neglecting some information by doing intensity measurements. If we are able to do some measurement that takes into account also the phase of the light, then we might be able to achieve more information from the same source. And this is what drove those recent advances. And the best thing to approach this problem is just by looking at what is the absolute best that we can achieve. And we have a very nice theory, as you all know, that is quantum estimation theory, that tells us exactly what is the fundamental limits, what is the maximum precision you can achieve, what is the minimum error you can achieve on estimating parameters, and also when you can achieve it. So if there's such a limit, are we able to actually achieve it by doing some feasible measurements? This is a problem that we can work out. So in quantum metrology, if we consider the general problem, we would want to use quantum mechanical features. As we said several times, we maybe need to not necessarily rely on enhancements of the sort, say, going from shot noise to Heisenberg limit, which is enabled with some other quantum resources like superposition and entanglement in the source. But already just being able to do the best possible measurement, even without other quantum enhancements, it's already helped, especially in this problem. And all these kind of quantum effects can improve the available precision in estimating parameters of relevance, like in this case, this separation. So if we now consider another wanted here, so quantum Schrödinger's cut to denote quantum effects. So the general paradigm is very simple. We have a probe state. In some cases, we can control it. In some other cases, it's given. Like if we have some source, then that's the source we want to measure. We cannot really change it. So this probe state undergoes a dynamics. This dynamics might be unitary or might be noisy, but anyway, it's generated by some quantum channel that imprints a vector of parameters on our state. So the output state will now depend on these parameters, and these are the parameters that we want to estimate. So in order to estimate this, then we have to do some measurement. Now, to make it a bit more general, I'm going to consider the possibility that we have to repeat this preparation and dynamics many times and then collect all these copies, because in some cases, the optimal measurement that we have to do is actually a collective measurement on all of these copies. Okay, but this is just to be pedantic. Once we've done this optimal measurement, as you know, by classical post-processing, we can construct an array of estimators for the parameters that we want. And what we're interested in is the covariance, so the sum of the variances of all the errors associated to each of these parameters. And what quantum estimation theory tells us is that this thing has a lower bound. So your error cannot go below this right-hand side, which is, apart from the statistical factor here, it depends on the number of times you repeat this experiment. This is just given by the trace of the inverse of this H matrix. And this H matrix is the famous quantum feature information matrix, whose elements can be defined from your state in terms of this other operator, which is called the symmetric logarithmic derivative, and it's implicitly defined by this expression here. So in principle, we can never achieve an error below this. Or now, in the case in which there are more than a single parameter, we are not even guaranteed that there exists a measurement that allows us to saturate this bound. If it's only one parameter, for instance, like in the case that I said, just one separation, then we know for sure that in the limit of very large number of repetitions, we can saturate it. In general, for multi-parameter case, this is not the case. So later on in our specific problem, we have to deal with conditions that enable us to confirm whether we can actually achieve this precision or not. But we cannot do better than this for sure. We might do worse, but not better than that. Okay, so using this apparently simple framework that many of you use all the time, Mankey, Tsang, and collaborators approached this problem. So we have, as I said in the beginning, 2 point sources on the same object plane, and we are interested in estimating in principle, it's already two parameters because it's a centroid, and these are the so-called angular separation and the angular coordinate of the centroid. You can easily show that the centroid can be estimated independently, so the only parameter which is problematic is this thing. Even with classical direct imaging, you can estimate the centroid with reasonable precision. But what did they find is that according to the quantum Cramer-Rao bound, if you calculate the quantum Fisher information, so very surprisingly, I would say very surprisingly, this is independent of the actual separation. So because it's a single parameter, you are guaranteed that there exists a measurement that allows you to estimate this distance with an error that stays constant with the distance, no matter how small it is. So if you do a suboptimal measurement, which corresponds to just photon intensity measurements, direct imaging, then what happens is, this is from his paper, so if you do this suboptimal measurement, these are the dashed line for the separation, the classical Fisher information of that measurement goes to 0 when you are in the sub-Rayleigh. I don't know exactly where Rayleigh is in these normalized units. I think it's around here. But this classical Fisher decays, which means that the error, which is the inverse, associated to this classical direct imaging, diverges. As we know, there's this curse. Okay, you cannot see anything. But this is just because the measurement is not good enough. So according to the quantum Cramer-Rao bound, there exists an optimal measurement such that this error is completely independent. So you resolve arbitrarily well, no matter how close they are. And in fact, the Fisher information stays constant. The error stays constant because it's just the inverse. And then these other curves here for the centroid. For the centroid, there's not too much advantage in going from classical direct imaging to the best thing. The scaling is more or less the same. You can resolve the centroid at arbitrarily small separation anyway. So that's not a big deal. But the big deal is on the separation. So that's why in this paper you read statements which are very strong, like, okay, quantum metrology kills Rayleigh's curse, and I think this is actually correct. And then they went a bit further because they studied specific measurement procedures that allow you to approach this error. So it's not just something mathematical, but you can actually do it with something that is not as horrible as the eigenstates of the symmetric logarithmic derivative, but there are a couple of schemes, and people have implemented them. So far, I think there have been 4 experiments. Actually, there have been more recently, another wave of experiments on this problem. And I know that some colleagues in Paris are also planning to work on this. So there's been a lot of attention on this problem. We wanted to go a little bit further. So what is it that we did? We considered, as I said, the possibility that the two sources are not aligned on the same object plane. And why was that? Because talking with these colleagues in engineering, they said that it's very problematic for them when they have to do surface measurements to resolve steep functions. So you can imagine that these two sources are actually maybe 2 emitters that have been put at the edges of a step or a steep surface on some complex sample that maybe they have generated by 3D printing, or it comes from, I don't know, whatever sample they want to precisely estimate. So we allow for this extra freedom, and so now our problem becomes a multi-parameter estimation problem with 4 parameters. Because we have, again, this, the 2 relative coordinates, which are the separation. So we have the angular separation, this is called S, but now we have a non-zero axial separation P, and then the relative coordinates of the centroids. So the angular centroid C and the axial centroid Z. To be honest, if you want to do the full thing, you have to consider the 3D estimation. So you have to consider also the other coordinate in the y-plane. You can imagine here, this is just a projection. And I have to say, Mankey, Tsang, and colleagues, they also consider the complementary 2D case, where they want to estimate x and y, but the two sources are still on the same plane. So if we just bring these two things together, I think we have the complete 3D estimation problem for the 6 parameters. But our student was so tired after he finished this that he didn't do it yet. Okay, but we can do it later. So we do this, and then we follow the same approximations that were done in his work, and there are some standard approximations there. So you assume that these point sources are thermal sources which are weak. And by weak, we mean that within 1 coherence time, they emit at most 1 photon. This is very standard in astronomy, fluorescent microscopy, and so on. So we imagine to do the experiment by dividing our observation time into many, many multiples of this coherence time, and in each of these little intervals, then we neglect the higher order photon contribution. So the state will just be a mixture of no photons or 1 photon. And then we are in the paraxial approximation, means that the detector is sufficiently far away from the source compared to the wavelength of the light. And then the shift invariant means that we can, without any loss of generality, I would say, consider the point spread function of the following form, where there is here a real term that only depends on the x coordinates, and then the phase information is factorized outside. We don't have to specify the specific form of this real term here. This will depend on the specifics of the lens. It could be a Gaussian beam, it could be sync, jink, depends on the shape of the lens and the aperture that we consider. But so far, the only thing, whenever I say our results are for general point spread function, I mean general complying with this factorization condition here. Fine, so then what we have to do, we have to calculate the quantum Fisher information matrix. And it was a very tedious calculation in the end, so I don't put any explicit details, but we have it in general in terms of the point spread function not specified. But if I want to give you some results, I'm going to specify one particular form of the point spread function, and the simplest that allows us to do fully closed analytical calculations is to consider the Gaussian one. So, yes? It's not, because they are, this one is a different one from this one.
You said that they are incoherent sources.
Yeah, but then in the propagation, this is further behind. And so when you can, so this diffuses more because it's behind. Okay, so Z1 and Z2 are different.
Yeah, but not because of the space factor, but because of the size are different, yes?
Yeah, I don't remember if this enters anyway, probably not. So that's just, okay. Okay. So, yeah, so we calculated this, and then if we want to give some examples, we specialize to the Gaussian case. And for the Gaussian case, the real part of the point spread function can be written in this way, where sigma 0 is the width of this Gaussian. So what can we find now? We can look at first of all, the diagonal elements of the quantum Fisher information matrix, which gives us each diagonal element gives us the individual error corresponding to the Cramer-Rao bound for each parameter separately. We don't know whether they are compatible with each other, but we can look at the individual estimation of each of them if it's possible or not. And results are good news. First of all, the most important one is the estimation of this angular separation is still unaffected by the angular separation. So this term of the quantum Fisher information is still constant with S. So again, there's no Rayleigh's curse on the angular separation, even though they might be with a non-zero axial separation. Actually, having a non-zero axial separation here, the dashed lines are when P is a bit bigger than 0, and the solid lines are the same as Mankei-Zhang, so the case P equals 0. Having a little bit of P helps in the estimation of this. I guess that just makes the sources a bit more distinguishable. So this is expected. And we can also estimate the axial separation. The important thing is that even though these orders of magnitudes look smaller than that one, but also depends on our choice of the wavelength and the sigma 0 and so on. But the important thing is, and this can be verified analytically, no one of these terms goes to 0 in the limit in which P and S go to 0. So even if these sources are arbitrarily close to each other, the quantum Fisher information diagonal elements remain non-zero. So the errors will always stay finite. It's not going to diverge. We can estimate in principle, so far in principle, simultaneously all these 4 parameters with a finite precision. But before I make this claim, I have to verify that actually they are compatible with each other. So if we look, in principle, there's no Rayleigh's curse, no cursing here. Let's see what happens with this compatibility. And this problem of compatibility has been studied in several references. I remember Matsumoto and Madeleine Guta, several papers looked at the most important criterion, which is when this Cramer-Rao bound can be asymptotically saturated. I think a very nice paper is a paper by Rafał and my former student Sami and Marcin Czarcina. It came out a couple of years ago, and they, let's say, very rigorously classify compatibility in terms of 3 conditions. So one of the conditions is not very relevant for us because, okay, there should be an optimal state that maximizes the Fisher information for all the parameters. This becomes relevant when you want to actually find this best probe to solve some estimation problem, but in our case, our source is fixed, so we don't have to bother about this condition. Second thing is, and this is the most important, there exists a single measurement that allows us to estimate all the parameters optimally, leading to the asymptotic saturation of the quantum Cramer-Rao bound. And the necessary and sufficient condition for this is that the symmetric logarithmic derivatives for pairs of parameters have to commute on average on our state. Now, if this state is pure, this condition is good because it also ensures that there exists, because the SLDs are not unique, so it ensures us that there exists some SLDs for each of these parameters that actually commute, really commute, not only on average. And so they have a common eigenbasis, and that common eigenbasis defines the measurement. When the state is mixed, this doesn't help very much. Just tells us that it exists, but it doesn't tell us how to construct that measurement. It might be, some, as I said in the beginning, it might be some complicated measurement on some entangled copies. Maybe there are some progress here. You can help me to do that. And then the third condition is also interesting because it deals with if you can gain in terms of resources when you want to estimate all these parameters simultaneously, instead of having to re-prepare your source many times and estimate them individually. If they are statistically independent, then you have a gain in terms of resources that is at most equal to the number of parameters that you want to estimate. I don't want to enter into this, but we can discuss it. It's explained very well in this paper. But to do so, then the quantum Fisher information matrix has to be completely diagonal. So let's see what happens in our case. As I said, this condition is not interesting for us because the source is fixed. You can consider other analysis, say what would be the form of the source that would make the resolution optimal. But sometimes you're just given a problem, then you have to look at that. So we don't care about this. This is something that surprised me very much. So this condition is always satisfied. It's always satisfied under all these assumptions that we had before, without having to specify the form of the point spread function. The state is always a rank 2 state, as I said, mixtures of 0 and 1. You calculate all this, and then effectively you find very simple things at 0 for all pairs of parameters. So there always exists a single optimal measurement that allows us to achieve that error which the Cramer-Rao bound gives us. So really there is no curse. We just have to find out how to unlock this, how to find the measurement. And this is also interesting. These parameters become statistically independent in the relevant limit, which is where these two separations are really small. So if they are arbitrarily close to 0, then the quantum Fisher information matrix becomes diagonal. This is a general result. This one, I don't know if it's general. We observed it for the Gaussian case. I suspect it's general, but we didn't do the calculation for the others more complicated point spread function. And so this is where we are. We have shown in principle that there is compatibility. We can estimate all these parameters with finite precision with some optimal measurement that I personally didn't find yet. I didn't look for it yet. So what is it that we have to do next? We have to go and try to construct a measurement that people can actually implement in the lab. So these are taken from a series of works by Mankey, Zhang, and colleagues, and I think variations of these measurements have been implemented. I had a conversation with Nicolas Treps a couple of months ago, and he said that this one, which is called spatial mode demultiplexing, which means decomposing the source into its Hermite Gaussian beams and then eventually detecting them separately. I think this one can be extended to our setting. I trust him. We will talk tomorrow. This one, it's an interferometric technique. I have to say that Mankey has also generalized it to 2D, but in the same plane. So we just have to maybe go and try to find out how to do this for our case. We just didn't do it yet. Yeah? But I think that I'm confident that we can find measurement procedure to estimate all these 4 parameters, approaching the precision given by the quantum Cramer-Rao bound, because we know it can be saturated, and we know we can get close to it. And so what are these applications I was talking about? So all these complex surfaces pose a problem for surface metrologists, especially those generated by 3D printers, because there are lots of ups and downs and steep surfaces, and they don't know what to do. So the head of this manufacturing metrology team was giving me this kind of example. So suppose that you're just going with the traditional, it can be contact or non-contact optical instrument that is going to resolve a situation like this. It will fail at the edges. So you will see this, this, and this, but you don't know how to do the edges. In principle, what I think is that because we know we can resolve arbitrarily close both these separations, so if we have emitters and we move them arbitrarily close and we do the proper measurement, this yellow blob here is something which we haven't defined yet. So I think we can resolve them completely and then bridge this gap. So my hope is that we will get there and eventually make this into some practical use, not just, I don't know. I like the fun of the quantum feature information and the calculations, but I think it would be nice if it actually, I don't know, gives some extra tools to people who do concrete stuff, yeah? Maybe some of you have some ideas about that. So yeah, so I think in this talk, which refers to the paper that appeared yesterday on Archive, we studied localization of two-point sources with more general feature compared to the literature, that they are on different object planes. So we have to estimate angular and axial components of the centroid and their separation. And then, interestingly, we show that simultaneous estimation of all these parameters is possible with a single optimal quantum measurement that is yet to be determined. It asymptotically saturates the quantum Cramer-Rao bound, and there's no Rayleigh scores in any of them. So the estimation remains with finite precision even when they are arbitrarily close to each other. Actually, in that limit, there's even a gain in resources because the problem becomes, the parameters become statistically independent. And the core results are independent of the form of the point spread function, but we gave simple results to illustrate them with the Gaussian case. And as I said, I want to investigate the measurements, try to do experiments as well with some of you maybe, and then look more carefully at what we have to do in order to develop this into a technique that maybe can be integrated in quality control for 3D printing and so on. So this is a picture of my group. People involved are Carmine, here depicted in the angular separation pose, and Thomas and myself. And then manufacturing metrology, there's Carmine again in this axial separation pose, and then Samantha and Richard Leach. So Carmine is a joint student between the two groups, and we hope that we continue this collaboration. Thank you.